Hello everyone, my name is Vaishnav from Dalhousie University. Today I'll be presenting our work on goal condition reinforcement learning for data-driven maritime navigation. So this is a joint work with my colleagues, Dilit, Samruddhi, Anand, Mahbub Alam, and my supervisor, Professor Gabriel Spaden, from the Faculty of Computer Science at Dalhousie University. So this will be the outline for our presentation, which will start with introduction, which will go to related works, the background section that discusses about goal condition reinforcement learning and action masking, the proposed framework architectural diagram, methodologies used, the RL environment and our reward designs, the results and discussions part, and finally we'll go through the limitations, future work, and conclusions. So let me start by motivating the problem we are addressing. Most of the world's goods travel by sea, which is over 90% of global trade relies on maritime shipping. So as shipping volumes continue to increase, so do our concerns about safety and environmental pollutions. So the core challenge in maritime routing is balancing between competing objectives. One is minimizing fuel cost by ensuring timely delivery and dynamically responding to environmental factors like wind. So this is a complex optimization problem that affects both economic efficiency and environmental sustainability. Going into the research gap that we have found, first is reinforcement learning is underutilized in maritime navigation, and existing studies does not highly make use of the automatic identification system, which is AIS data. Secondly, the current RL policies don't generalize well across diverse origin destination pairs. That is, they're either trained for specific routes or the trained algorithms can't adapt to new tasks without retraining them. So here is where we introduce MariNav, a framework designed to process large-scale AIS data for training reinforcement learning agents. So it enables the development of goal condition policies capable of generalizing across diverse maritime routes. So coming on to the related works, our work has several key differentiators. We are the only work that use real AIS data for creating a first-order Markovian graph that in turn will use will be used in RL training. While others rely on synthetic environments or simplified simulations, we integrate ERA5 weather data, while most prior works either use them in a synthetic fashion. We employ a multi-discrete action space that jointly selects both direction and speed, which is more realistic than approaches that consider only one control dimension. Finally, our use of goal condition RL enables generalization across multiple tasks, which is essential for practical deployment. So the key concepts behind our approach is goal condition reinforcement learning and action masking. In standard RL setting, an agent learns a policy tied to a single task and reward function. So this severely limits the generalization. That is, if you want the agent to handle a different task, you need to retrain it from scratch. Meanwhile, GCRL solves this by conditioning the policy on a goal variable, G. Instead of learning just a policy of action given a state, we learn a policy, action given state and goal. Next, action masking is a technique that works by restricting the policy to select only valid actions through a binary mask. Before the agent selects an action, we zero out the logits corresponding to invalid actions. So this prevents the agent from entering land-based cells, which would end the episode and also prohibit backtracking to the previous cell to avoid oscillatory behavior. So now let me walk you through our complete MariNav framework pipeline. We start with AISDB, our open source tool that processes and filters AIS trajectories from raw maritime traffic data. Next, we apply Uber's H3 hexagonal discretization over a shapefile to divide the navigation area into a grid of hexagonal cells. Hexagonal cells offer several key advantages for maritime navigation. Most importantly, they provide uniform neighbor connectivity, that is, all 6 neighbors are equidistant from the center cell. From the proposed trajectories, we construct a Markovian graph that captures vessel transition probabilities between cells. This encodes historical routing preferences. And then we integrate ERA5 wind field data to provide environmental context at each cell. Finally, we create a gymnasium-compatible reinforcement learning environment that incorporates action masking, and our designed reward function. So in this way, the environment is what the RL agent is trained on. For the dataset part, we focus on the Gulf of St. Lawrence region in the eastern Canada. Our dataset spans over a decade from 2013 to 2024, containing more than 10 million AIS records. For this study, we specifically filtered for tanker vessel data from August 2024. We discretized this region using H3 hexagonal grids at resolution 6, which creates 8,687 navigable cells. So each cell represents approximately 36 square kilometers of ocean surface. From the AIS trajectories, we built a first-order Markovian model that captures the transition probabilities between cells. That is how frequently vessels move from one cell to the other. For environmental conditions, we used ERA5 10-meter wind fields, providing both U and V components for August 2024 data. To explain our RL environment, we designed a state space represented by an 8-dimensional observation vector. So this includes the vessel's normalized latitude, longitude, its speed, the current wind direction, and the both start and goal coordinates, giving the policy all the contextual information it needs to navigate. Secondly, the action space is a multi-discrete action space. The agent selects one of the 5 possible maneuvers, which is essentially all the neighboring grids except the backtracking, and independently choosing one of the 5 speed levels ranging from roughly 8 to 22. Our reward function balances 8 key factors, all scaled by route distance for consistency. First, we reward progress towards the goal and encourage following a historically safe route from our AIS data, that is rprog and rfreq. We penalize wind exposure and fuel consumption, the latter using a physics-informed cubic relationship. We also include time and base penalties to promote faster and shorter routes. Finally, there is an invalid action reward, that is like entering a land would result in receiving a large penalty of negative 1900, though action masking typically prevents these. So our total reward is a summation of all these individual reward components. So for goal condition RL, we scale by the reference distance to normalize reward across routes of varying lengths, so that it ensures the agent learn consistently, whether navigating short trips or long ocean crossings. So the agent begins at a defined origin in a grid-based maritime environment and must navigate to a destination while avoiding land and minimizing penalties. So to understand what the design choice matters, we evaluate 9 PPO variants. So the first is with and without action masking to test the feasibility constraints. If action masking really would assist in faster convergence to reaching the goal. Secondly, history augmented observations to see if short-term memory helps. Third is intrinsic exploration using random network distillation to encourage novelty in sparse feedback areas. The fourth is using recurrent models such as LSTM to check whether temporal memory improves navigation. And finally, we use a penalty-only reward with no positive reward variant to test the importance of reward shaping. So our results demonstrate that action masking is essential for successful learning, and the overall masked PPO setting with reward shaping delivered the strongest performance, clearly outperforming all the other variants. So in contrast, PPO without action masking achieved a negative mean return. So the approaches such as adding recurrence or history augmented observations showed no meaningful improvement. So based on this, we hypothesize that our environment is already effectively Markovian. That is, the current state provides sufficient information for optimal decision making, and it does not require any additional temporal memory. So comparing against the classical baselines, our RL agent achieved the highest average returns when compared to A star, Dijkstra, and greedy approaches. So we also take historical routes into the baseline, and we can see that the historical routes had lowest performance amongst all the other baselines. And we think it makes sense because real vessels optimize for different objectives rather than complying to our reward function, such as scheduling to adherence or port availability and so forth. So for generalization, we evaluated on 6 routes totally, 3 that were seen during training and 3 new routes that were similar but not identical to training routes. The agent successfully transferred learning navigation skills to routes it had never explicitly been trained on, and this is where we see the importance of GCRL. So moving on to the limitations and the future work, first we plan to move from multi-discrete to continuous action space as we think it would better capture the continuous nature of real autopilot systems. Second, we plan to refine our fuel and drag models. And finally, modeling specific vessel dynamics such as the ship size and the handling profiles. We believe that it will allow for us to have more tailored routing strategies. And to conclude, we propose the first goal condition RL framework specifically designed for data-driven maritime navigation that will help us generalize across multiple routes. And by open sourcing our framework, we are also enabling the broader research community to advance maritime research. Thank you.